Hi, so today I will be taking you through a tutorial on how to use the nanoDDSCAT Plus tool. It's a 3-tool workflow that is used to generate a custom shape that is then put through discrete dipole scattering with whatever result parameters you would like. So the first stage is going to be viewing the tool screen. We have the 3 tool options, which we'll be doing 3D shape generation in Blender, followed by using the converter to convert the 3D object into the dipole format expected by DDscat, and finally running DDscat itself. There's also a 4th option here to download files at any point. You can just click it. It'll open up a secondary window which allows for upload and download. Every user is given approximately at least 1 gigabyte of space, which can be used for saving files from this workflow especially, and downloading them to the desktop. If there are previous runs you had, you could also upload them. So I'll start with Blender. We'll be making a custom shape, as that's the first stage. So we've actually modified Blender a bit to start up to a custom start page. What you see initially is just a basic cube and 2 lights that we've placed. One is for the Y polarization direction and one is for the incident light. These are values that you can choose to use, or you can use the default values set in DDscat. We decided that we would at least give you the chance to change them past the default graphically, as that's much easier than calculating them. So to start, we just have a basic cube. We can actually even delete this cube if we want. It's just there as a placeholder. And we can go about designing our system. So the easiest way to do this is by placing some of the built-in objects in Blender. If you're more experienced, of course, you can be able to really just draw about just about any shape you want. I'm not incredibly experienced, so I'm just going to be adding some shapes in. I'll add a cone. You can move it around however you like. And I will add a monkey. And perhaps I will also add a cylinder. So I'm going to be illustrating a few different concepts here. One of them is going to be overlapping items. So for the sake of this experiment, for this tutorial, I will overlap the cylinder with the monkey. Now notice that the first button that we provided as a custom button is to center the scene at the origin. This is done because DDA convert automatically centers the scene at the origin itself. So to get a realistic idea of where the incident lights are going to be pointing, it's necessary to center it within Blender. So this should happen automatically when you press the button. And everything is still in the same spatial relation to itself. It's just simply centered around 0, 0, 0. The next option that I can choose to do once I've got the scene that I want is to rotate the lights. So when I click rotate lights, it actually gives me a nice handy widget here that can allow you to rotate in any of the 3 radial directions it provides. And what it will do is it will rotate both the incident light and the polarization direction. So you can see, depending on where they are, you'll see either one or both of them moving, depending on which axes they may or may not be aligned to. Now, for a slightly easier use, it's best to really just set the incident light in this mode and ignore the Y polarization and set that in a later stage, which I'll go over in a moment here. So after setting the incident light, there's actually a 3rd button which will allow you to lock the incident light into place. So once you click it, the incident light won't move, and you're given basically the ability to rotate the Y polarization in the perpendicular direction to the incident light. So you can go over all the perpendicular directions that are available for that incident light angle. And really that's what you care about. So let's say I'm happy with this. It's not too different from normal. It's a little bit rotated off of the standard x-axis for the incident light. And really at this point I'm done designing the system. I think most users will probably be spending a lot more time designing the actual shapes they put in, and it's my hope that this process of exporting your scene out and into the DDscat is made as easy as possible within Blender. So the final object of this stage in the workflow is to literally export the object file to DDconvert, and that's done so just by the click of a button, and the object is converted. There's a status log at the top, so if you see any failures up there, you know that something's gone wrong. Really what it's doing in a nutshell is it's converting all of the objects into meshes and triangulating them. So that's a format that is required for the DDA-convert to work properly, and we handle all of that for you through the click of that button. What you can also do at the Blender stage is, if you wish, you can save your files. So these will save to your local workspace directory within the NanoHub workspace. And as I mentioned at the beginning of this tutorial, you can use the download and upload button to actually save these files to disk, or you can just leave them within your workspace and use them at any time that you would like. I'll go over as well where these files are placed and how they get shuttled along. As long as you're building something fresh, everything pretty much gets shuttled along for you. So let's move on to the second tool, DDA-convert. So after you press that button, you get an interface for the DDA-convert tool. And the first step of using this tool will be to choose an object file. So we can just click the drop-down menu, and we see that there are three options: to upload, to use a Blender file, or to use the sample object file. That's just a sample file we provide so that you can run something. Since we made a Blender file, we'll be choosing that. And if you choose upload, it will prompt you to send a file from your local workspace, your local disk space. The parameters below the object file choice begin with send this shape to DDscat main, and what that does is it designates this current run of the conversion tool to be the file that DDscat finds and uses. So if you don't always want to overwrite, if you want to save something while you're rerunning, then you will leave this on no. However, since we don't even have anything allocated, we'll currently leave this on yes. The second parameter is the longest dimension span in dipoles and spaces. This is probably the most confusing option in this tool, and if you do hover over these parameters, you'll get more explanation in a tooltip. I'll go over very briefly what this dimension means. You take the two farthest points in your entire system that actually have a real point in that space, and you measure that space, and this number designates how many points will be used to actually define that space. So the rest of the system is going to be affected by this. This basically sets the scale of dipoles to the ratio of the shapes. And this does include spaces. Spaces will be counted as dipoles even if no dipole is placed there. We also provide an option for a different file type output called the DX file output. This is something that is used as typically a volume type of file, meaning a shape volume data file. It can be used in programs such as VMD, the University of Illinois Molecular Dynamics program. It also gives you a option to define the scale between these points for the volume. With DDscat, we actually won't be defining the scale until the third tool in this workflow, so for now we won't really worry about that. and actually we don't really want a DX file for this either. I was just illustrating it. And displaying a 3D output of the converted shape is not necessary, but it can help you to have an understanding of what was just drawn. So definitely I will be turning this on. As well, there is another option for the 3D display as well as the output of the file to separate dielectrics for different shapes. So what this does is it takes each separate mesh, each separate shape that you defined, and it creates a different dielectric value for each shape. I'll also illustrate this point by selecting yes. If you don't specify it, then every shape is considered to be the same dielectric. This pops up one sub option which is hidden typically, which is to use inverted point allocation for overlapping shapes. So what this does is, in the case where two shapes are overlapping, the overlapping points get allocated to either one dielectric or the other, and if it's not the correct one, then flipping the switch will in turn flip which points are being allocated to the other dielectric. So I'm going to reduce this value just a little bit to maybe 40 so that we can get a slightly faster simulation to run. And with that I can go ahead. Really all the requirements that are listed below are taken care of within Blender for this workflow, since we automatically make your meshes triangular. So the first output file that we're displayed is the actual output file to DDscat. So to explain this real quick, there are going to be 3 dimensions. These are the dimensions of your system. If you only had one shape, these would be the dimensions of your shape. You're also given the number of dipoles that are used to build this shape, and as well a listing of each coordinate of each dipole that has been placed. This last column, icomp, defines which dielectric it is. So if we scroll down, we'll see a lot of them are allocated 1. When we find our second shape, it'll be allocated 2. And with the third shape, it's allocated 3. We can move forward and look at the 3D output, which is a little bit more visual. And what we see are the 3 shapes that we made colored in 3 separate colors. So there's a cylinder, the monkey head, and the cone. Now if we look closely at the cylinder and the monkey head, we'll see that the overlapping points were given to the monkey. The bottom of his face is still defined even though it was inside of the cylinder. If we go back and we flip the inverted point allocation, what we now see is that the points are being allocated to the cylinder, and the monkey's head, the bottom of it, has been cut off a bit. There's no visual cues for where the polarization lights were set in this figure. However, they are still in the Blender file if you want to go back and check the Blender file for those directions. There's also an output log for the conversion itself. This will tell you if there were any errors in the conversion. Typically, if you're seeing the DDscat output file in the 3D conversion image, then everything went right. There are a couple different things that can go wrong with drawing. One is if you don't use enough dipoles, the shapes will not completely draw. For example, if you specified a maximum length of 1 dipole, only 1 dipole would be placed instead of the 1,400 that were required. These are just some diagnostic values. That's what a typical output would look like. So keep in mind that Since we kept on the send this shape to DDscat main option, the second run that we created will be the one that's sent to DDscat, which we will now move to as the third and final part of this workflow. This is the DDscat interface. By default, you're shown an image of a rectangular prism as well as its dimensions. DDscat accepts both custom files as well as has some built-in shapes. So we begin by looking at the shape of the system that we want to run the simulation on. Again, you're given a chance to upload from your local disk if you would like, if you have a saved file. We can also import from DDA-convert, which is what we'll be doing. And additionally, there are a number of built-in shapes for standard prisms, ellipsoids, and cylinders. Choosing to import the shape will give you some slightly different options within the interface. These are pretty much the same as what you would get when you upload a custom file. The first thing you'll have to do is to define the scale of the system by defining the distance between two given dipoles. So when you went from Blender to the DDA convert point format, that was all still in a relative scale of ratios of the shapes to each other. So at this stage you actually define the scale of your entire system. So for example, if the maximum axis was 40 dipoles, if I want 1 nanometer per dipole, that would make my maximum axis of my system with scale to be 40 nanometers. If I set the distance between dipoles to be 2 nanometers, the maximum length would then be 80 nanometers. Moving on, there's the target rotations. These are in addition to rotating the incident light from inside of Blender. You can also rotate the object itself. This effectively amounts to the same thing, so if you set the lights properly in Blender, you probably won't want these additional rotations. However, they are there in case you want to fine-tune anything without having to go back to Blender. Since we use 3 dielectrics, we'll have to increase the number of dielectrics to 3. If you don't, you'll simply get an error and be requested to go back and increase that value. For the compositions, you can upload your own dielectric file. You can input a custom constant dielectric, or you can choose from this set that we've provided: copper, gold, platinum, silver. If we input a custom constant dielectric, we're given a new menu to actually enter in the constant refractive index there. And each one will have its own menu. So that completes stage 1 of DDscat. Next we can move on to the spectrum calculation. This is where we'll define the range of light wavelengths that will be sent at our target. Keep in mind that there are some specific limitations on the different built-in dielectric files of where we can guarantee their accuracy. Next we'll define the window of the minimum and maximum wavelengths that we want to look over. We'll do 400 to 500. And this window will be split into a number of sub-windows. So if I say wavelength window steps of 10, I would expect my results to be calculated at 400 nanometers, 410, 420, and so on. That's using a linear scale. There's also some other scales that are available for you. Additionally, we can also choose the polarization. So there is no polarization that's applied other than the default propagation along the x-axis. If you choose linear polarized y, it will use the value that we set in Blender. If you choose linear polarized z, it will choose a plane that is perpendicular to both the x and the y vectors which we set in Blender. Next we can move on to the near field. So for the near field we can choose to calculate either its regular value or the square of its value. And this value will be calculated at the maximum light extinction step that we found. So given the 10 wavelength windows, the one that's found to have the maximum intensity is where the E field will be found. We also give the availability for periodicity. This can be done in 1 or 2 dimensions, and this just repeats the shape infinitely and calculates the near field with this taken into consideration. When you choose to do 1 or 2D periodicity, you'll get a submenu opened, and this will allow you to set the object spacing in the 2 dimensions. So if you want it to be an exact shape-to-shape touching, you will use the same value as the length of your shape in that dimension. This distance is center-to-center spacing. So in the case of a system, it will be the center of the system. I actually won't be using periodicity here because it takes a long time to calculate. So we'll move on to the processing screen. Here you can choose either to use the local DDscat run simulation type, or you can send it parallelly to our remote servers on NanoHub, and you will be asked to set a time to allow for the processing, so you'll have to use your best estimate there. If the time ends earlier, then your simulation will come back incomplete. If it ends earlier than the specified time, then it will come back complete, sorry. If the amount of time is not enough to complete your simulation, then it will come back incomplete. So I will use the local DDscat because I think it will take less than 12 hours and it's not a gigantic shape system. And we can just simulate. You'll get a quick output log. This is basically what is being input into DDscat through the typical command line interface that you would have to use if you weren't using this tool. So you can see the basic parameters that we set. The custom dielectrics were the constant ones that we defined. The first screen that you'll see on the output screen for DDscat is the results. So if you have any errors, we'll automatically paste them here for you, along with the description of why the error occurred. This one went successfully, and it tells us that the maximum wavelength value was at 0.5 or 500 nanometers. There's a number of different output menus to observe in DDscat. The first 3 are graphical, and they give us the different light extinction, light absorption, and light scattering that we have. If you hover over the graph, you'll see each point can be highlighted at its values there. If you use more wavelength window steps, this will become a smoother curve. Next, you're provided with the text files for the actual near fields that we calculated. These are in case you want to download them and use them in another program. That's given for the regular E field, and then we also provide the log scale of those values. Next, we have the graphical view of the 3D electric field. So we can see where our cylinder was. Actually, if we move these cut planes, we can go over the area where all of our shapes were. So if we go down far enough, You see some kind of emission from the cone as well on the left. The emission from the cone seems pretty weak. That's probably because of as a result of the dielectric we used. Next we can look at the actual field itself. So again, it looks like the only thing we are seeing is the cylinder, as that was something that we chose to be a constant or a built-in dielectric. If we increase the number of isosurfaces, we can start to see the finer aspects. With 4 isosurfaces, we can see something from the cone appearing. This just splits the intensity scale to have more possible drawn values. The log scale is a similar thing, but with a slightly remade scale for the maximum and minimum and the points involved. So this will change the coloring scheme, as well as provide some slightly different outputs in terms of the visualization view. There's also some timing information given for how long the simulation took at each step. This will help you to get estimates for future runs of how long things might take. And then there's the typical DDscat outputs that are generated by itself, the M table, as well as the Q tables. These values are reported in other formats in our output. There's also the target, which is exactly what came out of DDA-convert, and the parameter file, which we saw during the loading screen, and finally the output log from DDscat itself. So again, if there are any errors, we would report them to you, so we pretty much know that this ran successfully. If you wanted to go through it by hand and see some of the more finer details of how the calculation was working, we provide that through this output log. And that's it. So again, at any stage within these Rapture tools, you can always download whatever output menu you're currently looking at. This will give you a prompt to download it to your desktop as is, as a text file for the text outputs. And for the 3D outputs, it'll give you the option to download as either a VTK or an image file. This should allow you to save files at any stage, any inputs, such as the ones from DDA-convert, if you wanted to upload them later instead of following the whole workflow. Thank you for your time, and I hope this tutorial is informative and insightful. If you have any questions, please feel free to contact us, post in the questions or wishes areas of this tool, and also you can refer to the separate tools within here, such as the DDA-convert tool and the DDscat tool, and see their questions and wishes pages to see if your question has already been asked. Thanks once again,